Alright, so in chapter 15, we're going to talk about the rules of probability. Okay? And the first rule we're going to talk about is independence. And we already know when two categorical variables are independent of each other, then back in chapter 3 when we drew a segmented bar chart, the distribution of the variables is equal across categories. Okay? So if I look at males here, there's 100 males and there's 80 females. Okay? And if I look at the distribution, and when I talk about distribution, I'm talking about percents. Okay. So in males, blue eyes, that's 30%, 40% brown, 20% green, and 10% other. And then for females, 24 out of 80 is 30%. And then 32 out of 80 is 40%, and 16 out of 80 is 20%, and 8 out of 80 is 10%. So in that case, the distributions are equal. Okay. So test number 1 is the categorical distributions are equal for both variables. So we looked at that. We said, oh, these are both 30%. These are both 40%. These are both 20%. And these are both 10%. Okay, so if the categorical distributions are equal, like we looked back in chapter 3 when we drew segmented bar charts, then we would say that eye color is independent of gender. Okay? Well, another thing that we could do is we could add up all these going down, and this would be 54. And this would be 72, and this would be 36, and this would be 18, and this would be 180. Okay. And if we already know that the distribution for males and females is this. But now what's the marginal distribution? Okay, the marginal distribution, if we do 54 divided by 180, we would get 30%. And I'm just going to put total here. And then 72 out of 180 is 40%. And then 36 out of 180 is 20%. And 18 out of 180 is 10%. So, if I compare male distribution to the marginal distribution, this is a conditional distribution, okay, or a categorical distribution, and this is a marginal distribution. So if I compare one of the categorical distributions to a marginal distribution, they're also the same. Okay, so the categorical distribution across one variable equals the marginal distribution. So if I compare male to the margin, they're equal. If I compare female to the margin, they're equal. Okay. So, in this case, we know that the probability, we would write this as the probability of A given B. So, probability of blue eyes given that they're male equals the probability of A, probability of blue eyes. So, if this equals this, we know we're good to go. Okay. So, that is one of the rules we have to know for probability. Okay, so if the categorical distribution equals the marginal distribution, then we have evidence of independence. And then the last test is from last chapter. We said, oh, if two events are independent, then what do we do with the two events? Well, we multiply their probabilities. So the probability of A and B equals the probability of A times the probability of B. So conversely, if we know that the probability of A and B equals the probability of A times the probability of B, then A and B must be independent. Okay? So, let's look at that. The probability that someone is male, let's see, we got 100 out of 180. Probability that somebody has blue eyes is 54 out of 180. Okay, the probability of male and blue eyes. Male and blue eyes is 30 out of 180. So what is the probability of male times the probability of blue eyes? Well, it would be, we would do 100 divided by 180 times 54 divided by 180. And if we do those, we get 0.1667. Well, what is the probability of male and blue eyes? Well, it's 30 out of 180. And that's also 0.1667. So what we said is the probability of male times the probability of blue eyes equals this, and we know that the probability of males and blue eyes is this. Since those are equal, we can say that eye color is independent of gender. Okay? Okay, these events are independent because the probability of male times the probability of blue eyes equals the probability of male and blue eyes. So, if the probability of A times the probability of B equals the probability of A and B, then A and B are independent events. Alright, the next thing we're going to look at is what we call conditional probability. And the way that we read this is we say that this is the probability of A given B. Okay, now B is the condition. B is the condition that we're looking at, and we're looking at all of the A's that meet the condition. Okay, so the probability of blue eyes given that they're male means the probability someone has blue eyes given that the person is male. Now, male is the variable is the variable that is the whole that we look at. We're looking at males. That's the condition. So what do we got? We have 100 males. That's what it's telling you. When it writes this, it says look at the males. That's the condition. And blue eyes is the category within males that we look at. So we say, oh, okay, let's look at the male row. There's 100 of them. How many of them have blue eyes out of that 100? 30. So it's 30 out of 100. So the probability that someone has blue eyes given that they're male is 30%. So that equals 30 out of 100. Okay. The numerator equals 30, which is the cell probability of male and blue eyes, which, by the way, is if you were to look at just male and blue eyes, it would be 30 out of 180. The denominator is 100, which is the probability of male, which is 100 out of 180. So, the probability that someone has blue eyes given that they're male, the blue eyes goes on top, and that's 30 out of 180. And the male goes on the bottom, which is 100 out of 180. And if you divide a fraction by a fraction, you wind up doing keep, change, flip. So you would do 30 out of 180 times 180 over 100, and the 180s cancel and you get 30 out of 100. Okay. So this will also work for percentages. Now what I just did, that is the formal definition. The probability of A given B is the probability of A and B over the probability of B. So you'll see this given as a formal definition. However, when you have a contingency table given, it's pretty easy to do these, okay? Because all you do is you look at this condition and you say, oh, okay, well, we're all the males, so there's 100 of them. Oh, how many of them will have blue eyes? Well, 30. Okay, what if I was to do it with females with brown eyes? Probability of brown eyes given that they're female. Well, I go and I look at the females. That's the condition. There's 80 of them. How many of them have brown eyes? 32. So it's 32 out of 8. Okay, this formal definition we will use when we have to. But in general, we will just use the contingency tables to answer these questions. Okay. So this in here was kind of a derivation. Okay, as long as you understand the concept of conditional probability, that that's your condition and you're looking for this many within that condition, you'll be okay. So this also works for percent. Let's see, blue eyes in male. Let's see, that's 30 out of that's 30 divided by 180, and that's 0.167. And the probability that they're male, that's 100 out of 180, and that's 0.556. And if I do 0.167, which is this divided by 0.556, what does that equal? That should equal 30%. So it's 0.167 divided by 0.556, and that comes out to like 30. We rounded, so it's 30%. So all I did is I did this using these percentages, okay, or decimal. I changed the percentage to a decimal. Okay. All right. So this definition here is on your AP formula sheet, by the way. You do not have to memorize that. However, this definition here is not, and you do have to know how to test for independence. And it's very simple. You need three things. You need the probability of A, you need the probability of B, and you need the probability of A and B. And if this formula jives and they're pretty close to each other, then you have evidence of independence. If not, then you have an association. Okay. Alright, so let's look at problem 1 here. Now whenever we have a contingency table, the first thing I like to do is get the marginal totals, and this is 18, and let's see, that comes out to 135 plus 18 is 153, and that's 75, that's 85, and that's 68. Okay, so there's our marginal totals. So the probability somebody's a Yankee fan is pretty simple. We look at Yankee fan, that is a column. There's 90 of them, and there's 153 people. Okay, this should be Yankee fan or Red Sox fan, or. So those are disjoint events. Yankee fans are not both Red Sox fans, and Red Sox fans are not Yankee fans. So what do? We add. So we do 90 out of 153 plus 45 out of 153 equals 90 plus 45 out of 153. And it comes out to 135 out of 153. Now, here's our conditional probability. Yankee fan given that they're female. Well, here's the condition right here. Females. Well, where are all the females? There's 68 of them. And of those 68, how many are Yankee fans? 40. So it's 40 out of 68. That wasn't too hard, right? I did all those derivations and everybody's like, what's going on? It's not as hard as it seems. Okay. Is baseball fan independent of gender? Okay, so our test is the probability of A times the probability of B equals the probability of A and B. So what do you have to pick? You have to pick a gender and you have to pick a team. So you can do, you have 6 different options here because you have 3 for males and 3 for females. You can use any one that you want. Okay, so I'm going to use female and Yankee fans. So I'm going to do the probability of female times the probability of a Yankee fan equals the probability of female and Yankee fans. Are those equal? So females is 68 out of 153. Probability of being a Yankee fan is 90 out of 153. Probability of being female and a Yankee fan, be careful, this doesn't say female given that they're a Yankee fan, it's and. So that's going to be 40 out of 153. So we're going to go to our calculator and we're going to do 68 out of 153 times 90 out of 153. Put it in parentheses. Okay, and that comes out to 0.261. And then I do 40 out of 153. That comes out to 0.261. Since they are equal, I say it appears that baseball team is independent of gender. Well, what does that mean? It means that the same percent of males that like Yankees is roughly the same as the same percent of females that like Yankees, and the same thing for Bo Sox and the same thing for Mets. Okay, and we already tested that in our introduction when we went over independence, so we knew that that was true for this. Okay, now we come into another issue, this problem right here, probability of Yankee fan or male. Well, are those disjoint events? Well, you're adding this column because those are all the Yankee fans, and you're adding this row because those are all the males. So do I simply add 85 plus 90 and put it over 153? Well, from simple math alone, you would have 175 over 153, and that doesn't work. So here's the problem. They're not disjoint. You have males that can be Yankee fans. It's not like Yankee fans and Bo Sox fans. If I was to say probably being Yankee or Bo Sox, they're none in common. When I say male or Yankee fans, there's this many in common. So when I add 90, I have the 50 in it. And when I add 85, I have the 50 in it again. By the way, what does that represent? That represents male and Yankee fans. So what happens is I've counted that 50 twice. So really what I have to do is I would do 90 out of 153. This is all out of 153 plus 85, but I got to subtract 50 because I counted 50 twice. So when I do that, I get 125 out of 153. So when events are not disjoint, probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. And A and B represents those common elements that are in this row and in that column. Now, how could you tell if events are disjoint from a contingency table? Very simple. If you're adding column plus column, then they're disjoint because columns don't have anything in common. But if you are looking at a row and a column, they're going to intersect, and those are not going to be disjoint unless this is 0. Okay, and very rarely will that happen. Okay, so That's how you tell if events are disjoint or not disjoint. If you add a column to a row, if you add this row total to this column total, you know you're not dealing with disjoint events. But if I was to say, okay, Yankee fans, that's a column, Bo Sox fans, that's a column, those have nothing in common. The last one, probability of male given that they're Mets fan. Okay, well that's the condition. Well, how many Mets fans do we have? Got 18 of them right here. And of those 18, how many of them are male? 10. There are 10 out of 18. Okay? Alright, problem 4 here. The makeup of AP students and students involved in after-school activities at BMHS is shown in a Venn diagram. Okay, now what a Venn diagram does is it's a way of capturing elements that are involved in two different categories. Right, so we're comparing after-school activities to AP courses. Okay. So the first question is, are after-school activities and AP courses disjoint? And the answer is no, because 20% of students do after-school activities and AP courses. By the way, that's and right in the middle. Okay, so point due equals the probability of after-school activities and AP courses. If you have an and, you don't have disjoint events. Okay, a disjoint events means you could do one or the other, but not both. And there are students that are doing both, so those are not disjoint. The second one is the probability people are involved in after-school activities. Now be careful. If you look at the graph and you want to say 0.4, that's a typical mistake. But if you look at the after-school circle, you have this 0.4 and this 0.2 that are in this circle. So if I was to say just after-school activities and nothing else, that would be 0.4. But there are 0.4 that are involved in just after-school activities, and there are 0.2 that are involved in after-school activities and AP courses. So that equals 0.6. Probability someone takes an AP course. Well, again, you might be tempted to say, oh, 0.13. Well, that's the 0.13 is the people who take only AP courses but don't do after-school activities. But there's 20% that do both. So this 0.13 has to get added to that 0.2. And that's 0.33. Okay, so this is or again. Or no, this is and. Alright, so that's or. Alright, let's do and first. This one should be done first. This is the and one. And is easy, and is always in the middle. That's very simple, it's 0.2. Now, Venn diagrams offer us, when we're doing or, that offers us two ways to do this. Remember, or is the probability of A plus the probability of B minus the probability of A and B if they are not disjoint events. So I could do it like this. The probability of after school is 0.6. The probability of AP is 0.33, but I counted the 0.2 twice. Okay, the 0.2 is in the 0.6 and the 0.2 is in the 0.33, and that comes out to 0.93 minus 0.2, which is 0.73. Or the other thing I can do is I can just add up these three numbers, 0.4, 0.2, and 0.13, and that also equals 0.73. So a Venn diagram makes or very easy to do. Okay. By the way, if this is 0.73, then what would be out here is 0.27. Well, what does that represent? if the probability of doing after-school activities or an AP course is 0.73, then the 0.27 represents the percent of students to do neither. Okay, they don't do after-school or an AP course. Okay. Are taking AP courses and being involved in after-school activities independent? Well, we got to do the probability of A times the probability of B equals the probability of A and B. Okay, well, what's A? And that's after-school activities. Now you got to use the 0.6. Probability of B is AP courses. That's 0.33. Probability of A and B is right in the middle, 0.2. So we do in our calculator 0.6 times 0.33, and you get 0.198. Now, alright, so this, I'm going to use this little wavy equal sign, which means approximately. In real life, guys, things don't always work out perfectly, and this is one of those cases, okay? This is close enough. Now you say, you're going to ask the question, I know, well, how close is close enough? Usually within a couple percent. Now this is within 0.002. Okay, so within 0.002 is certainly close enough, but I'm not going to write a dogmatic statement here. I'm going to say something like, it appears. Okay, so I'm writing kind of a soft statement that students who take AP courses is independent of taking after-school activities, or being involved in after-school activities. You wouldn't take it. You could have written that a little bit better, but you get the point. Okay. I don't say, because these are close, I don't say, oh, taking an AP course is independent of being involved in after-school activities. No. Okay, this is pretty close, so I'm going to say, to me, it looks like this is true. Okay, it looks like this is true. Okay. All right. Now we got to do conditional probabilities. The probability of being involved after school, given that they take an AP course. Okay, well, that's the condition. How many take an AP course? 0.33. Let me just put this down here. There. All right, so AP course is 0.33. How many of these 0.33 are involved in after-school activities? 0.2. Okay, 0.2 of those 0.33 are involved in after-school activities. And if you do that on your calculator, you'll get 0.606. Takes an AP course given that they're involved in after-school activities. Well, there's the condition. What do we know about after-school activities? Well, we know that's 0.6. So that goes on the bottom. That's the group that we're looking at. And how many of those 0.6 are involved in an AP course? All right? Well, we go down and we say, oh, okay, how many of these are involved in an AP course? 0.2 again. And that's 0.3 repeated. And then the last question is what we already found out. Probability a student is not involved in AP or involved in after-school activities. That's this number right here. That's that 0.27. Okay, and it's simply you do or and you subtract it from 1. So it's really 1 minus 0.73. And that 0.73 was this one right here. Okay? Alright, so let's look at problem 5 here. We have the probability a student owns a car is 65%. The probability a student owns a computer is 82%. And the probability they own both is 55%. Okay. So we got to create a contingency table and a Venn diagram. So basically what we have is we have that a student owns a car. So that means that they would not own a car. So we'll do own a car, not own a car. And then they own a computer, and they not own a computer. Now whenever I'm given percentages, I just like to do it out of 100. So I'm going to create a contingency table that looks like this. And then my total is going to be down here. So what I know is the probability a student owns a car is 65%. So that means that 65 out of 100 own a car. So that must mean that 35 do not own a car. And 82% own a computer. So that must mean 82 are down here, and 18 would be here. Okay? And the probability they own both is 55. So that 55 goes here. Okay? And then we can just fill in the rest of the box. Well, 55 plus what is 65? That must be 10. 10 plus what is 18? Well, that must be 8. And then I could say, okay, well, this must be 55 plus 27 is 82, or 27 plus 8 is 35. So we set up a contingency table for this situation. Another way we could do it is with a Venn diagram. Okay, now a Venn diagram, I do this. So this would be the computer people. No, that's the car people, and this is the computer people. Okay, now when I start with a Venn diagram, I always start in the middle right here. That's the and that would be 0.55. Now the car is 65%, but we already have 55% in the car circle, so we need 10% more. And the computer circle is 82%, but we already have 55%, so that must be 0.27. So then I add these three up, and this would be let's see, 0.65. So that would be 0.85, 0.92. So that must mean that 0.08 are out here. And those are people that neither own a computer nor a car. So the probability of a car and a computer, if I look at the contingency table, it's 55 out of 100. Or I could look right here in the middle of my Venn diagram, and that's 0.55. Now this is car or a computer. Now are these disjoint events? Well, no, they're not. Why? Because you can own a car and a computer. So I got to use my non-disjoint rule, which we learned in a previous problem. Right? So A or B is the probability of A. So the probability of owning a car is 65 out of 100. Probability of owning a computer, 82 out of 100. But you could see in this 65 and that 82, I counted 55 twice. So I got to subtract that out. So that becomes 92 out of 100, which is 92%. If I did it using the Venn diagram, the easiest way to do it using the Venn diagram is just to add up these three, and then you would get 0.92. Okay, so car, given that it's a computer, that's the condition. So I look at my contingency table. How many own a computer? 82. Yeah. Of those 82, how many of them own a car? 55. If I do it with the contingency table, the the percent that own a computer is right there. That's 0.82 on the bottom. And what percent own of those 0.82 own a car? That would be 0.55. So you can see we're really doing the same thing, but we're just doing it with decimals. Okay, so those two are equal. Actually, not approximately, they are equal. Computer, given that they own a car. Okay, so that's my condition. How many own a car? 65. And of those 65, how many of them own a computer? 55. Okay. If I do it with the Venn diagram, this the percent that own a car is 0.65, and of those 0.65, how many own a computer? 0.55. So those are the same. Are owning a car and a computer independent? So we do the probability of A and B equals the probability of A times the probability of B. Well, the probability of owning a car and a computer is 55 out of 100. Probability of owning a computer, 82 out of 100. Probability of owning a car, 65 out of 100. So let's do the math. We do, let's see, 82 divided by 100 times 65 divided by 100. And that comes out to 0.533. Now, we look at that and we say, oh, this is 0.55 and this is 0.533. Those are pretty close. Okay. So, again, I'm going to write kind of a soft statement. Okay, they're not exactly equal, but they're pretty close. So I'm going to say it appears that owning a car could be independent of owning a computer. Okay. So that, you know, again, with things being that close, you know, it's a possibility. I wouldn't, you know, we don't definitely know it is, and we definitely don't know it isn't. It's in a gray area, so we kind of write a gray area statement. Okay, and that's fine. And then the last question. Nope, we're done. That's it. Problem 5. Alright, so problem 7. This is kind of a common problem on the AP. They give you one probability and then another probability, and then they give you an or, not an and. So you got to create a contingency table. So we have basically two conditions. We have A and then not A, and then we have B and not B. And there's our contingency table. Okay, and we'll always do it out of 100. So A is 0.5, so that would be 50, so not A must be 50. And B is 0.3, so that would be 30, and not B would be 70. Now the first thing we need is A and B. Okay. Now what do we know? We know that A or B is 65%. Okay. Well, if these were mutually exclusive, this plus this would equal that. Well, they don't. So there's some overlap. So remember, your rule, if events are not mutually exclusive, is we add them and then we subtract out and. So the probability of A or B we know is 0.65. So we'll say that's 65 out of 100. The probability of A is 50 out of 100. The probability of B is 30 out of 100. Minus X over 100. We don't know what that is yet. Obviously you could figure this out pretty easily. So this is 80 over 100 minus x over 100. Well, what does x have to equal? It's got to equal 15. So that must mean that there are 15 that are a and b. So that must mean not b is going to be 35. Not a is going to be 15. 15 and 15 is 30. And then this here, 15 plus 35 is 50. 35 plus 35 is 70. So there's our contingency table. So I think we answered this question. Are A and B mutually exclusive? Well, the answer is no. If they were, A plus B would equal A or B. This would equal 0.8, but it doesn't. So there must be some overlap there. Alright, so a contingency table, to do this, we would do this up here. Okay, so again, the first thing you have to find is and. So again, you would use your rule and you would say, oh, 0.65 equals the probability of A plus the probability of B minus the probability of A and B. And we don't know what that is, but we do know that 0.65 equals 0.8 minus the probability of A and B, and we already figured this out. This is going to be, probability of A and B is going to be 15%. Okay, so the probability of A and B equals 0.15 because 0.8 minus 0.15 equals 0.65. So that goes in the middle. And this is A and this is B. A is 50%, but we already got 15% in that circle, so this is 0.35. That's let's say, yeah, that's 0.35. That's just A. And then B is 30%, but we already have that in there. So we add another 15%. And if we add these across, we get 0.65. So that must mean that there's 0.35 that are neither A or B. Okay, so now we already figured out A and B right here. It's 15 out of 100. It's that right there or that. So it's 15 out of 100. 15%. A given B. This is why contingency tables are so much easier, right? The condition is B. How many are in B? Well, there's 30 that are in B. And of those 30, how many are in A? 15. Now, if you do it with the Venn diagram, you say, well, how much is in the B circle? 30%. And how much of that 30% is in A? 15. So it's 0.15 over 0.3. B given A. Now, the condition is A. There's 50 in A. How many of those 15 are in B? 15. Using the contingency table, you say, okay, we're doing B given A. In the A circle, there's 0.5. How many of those 0.5 are in B? 0.15. So it's just winds up in decimal form. Same thing. Okay. Are A and B independent? No, again, you got to use your rule. Probability of A and B equals the probability of A times the probability of B. Well, we know that A and B is this 15 out of 100. Probability of A is 50 out of 100. Probability of B is 30 out of 100. Now we do the math. So it's really, we can just multiply 0.5 times 0.3 here. And we get 0.15. And this is 0.15. And this is 0.15. So now I can just make the statement. It appears that A and B are independent. Alright, so let's look at problem 9 here. And we have a problem. A Science magazine reported on a new computer-based test for ovarian cancer that examines a blood sample for the presence of a certain pattern. protein's ovarian cancer, though dangerous, is very rare, affecting 1 of every 5,000 women. The test is highly sensitive, able to correctly detect the presence of ovarian cancer in 99.9% women who have it. However, it is unlikely to be used because it gives 5% false positives. Alright, so this is a little bit different than problems that we've looked at before, in that the probability changes based upon a previous condition. Okay, so we cannot do a Venn diagram on this one. However, we can still do a contingency table. Okay, contingency tables still work. So the person either has cancer or does not have cancer, and the test is positive, or the test is negative. Okay, so that's how we would set up our contingency table. Now, most of the time I do contingency tables, I like to do based off of 100. Okay, but the problem here is this 1 of every 5,000 is very small, and this 99.97% is a decimal percentage, and that means that the other percentage is going to be 0.03%, which doesn't excite me either. So I'm going to work with this 5,000 here. I'm just going to make my total 5,000. It just seems I need a bigger number than 100, so I'm going to work with that, and it's probably going to still wind up working with decimals, but they won't be as small as if I worked with 100. So we know that 1 of every 5,000 has cancer. So that must mean that 49.99 do not. Okay. And it says the test is highly sensitive, able to correctly detect the presence of ovarian cancer in 99.97% of women who have it. So for every 1 woman that has it, 0.9997. Okay. It would pick up the it would correctly pick it up. So that must mean that this here is going to be 0.0003. So that would be an incorrect test, by the way. So they have it, but it shows negative. Okay. And then we have this 5% here. 5% are false positives. So of the 49.99 that don't have it, 5% of them are going to test positive. So we're going to do 0.05 times 49.99, and we get 249.95. And if we then subtract that from 49.99, we get that this must be 4749.05. So now we just we got to do some adding. So we do 0.9997 plus 249.95, and this comes out to 250.9497. And notice I am not rounding, because that may throw the percentages off a little bit. So I'm going to leave these just as they are. So this is 4749.0503. And if I add that to 250.9497, we get 5,000. So everything adds up. So that's one way of doing that. Again, I like doing contingency tables when we can do them. It keeps things consistent. Now another tool you can do is you could do a what's called a tree diagram. And the tree diagram looks like this. We know that as far as people who have cancer, we know that it's 1 in 5,000. So that must mean people who not have cancer, that's 49.99 in 5,000. Okay. And of the 1 in 5,000, the people that will test positive is 0.9997, and the people that will test negative is 0.0003. And then for the people who don't have it, 5% of them will test positive. And then obviously 95% of them will test negative. Okay. And then what I do is I just multiply all these across. I got to multiply 1 in 5,000 times 1 in 5,000 times 0.9997, and that's 1.994 e to the negative fourth, so that's 0.00019994, and then I got to do 0.00303 times 1 in 5,000. That's 6e to the negative eighth, so that's 0.00007. Let's see, 5, 6, 7, 8. Then I do this times this, so 0.05 times 49.99 divided by 5,000, and that's 0.04999. And then I do 0.95 times that, and that's 0.94981. And I'll show you how all this works. Okay, just a different approach. So you use a tree diagram when the probabilities change upon a previous condition. So the probability that the test will test positive changes whether they have cancer or don't have cancer. It's 99.97% of the time when they do, and 0.05 when they don't. So that would be the tool that you would use, or you could just stick with a contingency table, which is kind of my choice. That would be my tool of choice, since we can use contingency tables for just about everything. So now we have this question: determine probability that a woman who tests positive using this method actually has cancer. So we're looking at this probability that they have cancer. Given that they, oh, well, I think I did that backwards. Okay. So, yeah, so they have cancer given that they test positive. That's what it is. So we're looking at the test positive, that's the condition. So we got 250.9497, and out of that 250, how many of them actually have it? Well, it's 0.9997, and if I divide those, it's going to be very small. And it's like 0.004. Well, that's not a real good test. I mean, if you get a positive test back on this, less than 1% of people actually have it. So you have like 99% of people running around thinking they have this and they actually don't. So this test is not a good test. Okay. And the way I would do it with the tree diagram is, okay, we need probability that they have cancer given that they test positive, right? We're going to get the same answer, just a different way. So the test positives, guys, is this and this. So that's what has to go on the bottom. We do 0.000199994 plus 0.04999. Now, how many of them have cancer and tested positive? Well, that would be this group right here. This group right here. It would be 0.0. And what you're going to see is this should come out to be about the same thing. Okay, so we do the math out, and we get that 0.004 again. Okay, your book does it this way. I have, if that's the way you want to do it, that's fine. I prefer, personally, to just stay with contingency tables. That way you have one tool that does everything. You don't have to worry about, okay, well, this situation I do a Venn diagram, this situation I do a tree diagram. Put everything into a contingency table, and then you just have one tool that covers everything. Okay? Alright, let's look at problem 12. Math SAT scores can be modeled by a normal model 500 with a mean of 500, so that's mu, and a standard deviation of 100. Okay. So find the probability that a student scores 700 or more given that they scored at least 600. So this is the probability of 700 or more given that they scored at least 600. So this is the condition. Okay. So we have to go into our second distribution, norm CDF, and they're going to score at least 600, and we'll make the upper bound they would score and the mean is 500, and that would be 0.157. So 15.7% of students score between 600 and 800, and we want in that region the group that got 700 or more. So we got to do so let me draw a picture of this for you. Here's what we're looking at. There's the mean, right? We're looking at this group of kids. So we're looking at only that group of kids. But within that group of kids, we want to know what percent. So in other words, what percent is this shaded area right here of this entire shaded area? Because it's a conditional probability. We're not looking at all students. We're only looking at students who scored 600 or more. So what we determine is basically of every 100 students that take it, 15.7 roughly will score 600 or more. And of those students, we would say, okay, let's say we do norm CDF. We say, okay, how many of those students would get a 700? And that would be 2%. So we say, okay, let's do this divided by 0.157, and we get about 14%. So 14% of students who score at least 600 will get 700 or more. Okay. This 0.021 represents the percent of all students who score 700 or more. This represents the percent of students, of all students who score 600 or more. But of these students that score 600 or more, okay, 14% of those students will score 700 or more. And that's how you would do that problem. So it's best if you draw a picture first. It kind of helps you to understand it.